Welcome. We're going to be talking this morning about Smith version 4.1. Smith version 4.1 is a Windows-based visualization tool and a computation tool, by the way, that we can use in conjunction with the Smith chart to let us see the effects of some different changes we can make in our circuits. In particular, in this case, in building L matches, which is what we talked about earlier in this slideshow. So let's get the software launched here. It only takes a second to come up. We're going to start by plotting the same point that we've been working with all along. We've been working with one particular impedance, and that impedance starts out as 33 with a minus J of 51. So we'll come up here to the keyboard entry point, and we'll type in 31, hit tab, minus 51, and say OK, and that'll plot the point. Now, that point should be in a familiar space to us. That's the area where we've been working all along. In this software, I don't have to denormalize. I just put in the actual measured values that we would get from our analyzer. So in this case, I put in the 33 and the minus 51. The J is understood. However, I did set the frequency at our 14.2 megahertz that we've been using all along, just for consistency. If I click OK after entering the values, the real value and the imaginary value, the plot point just pops up on the screen right where it's supposed to be. And as you can see, it's in the same general area as we had seen it before. It's just right about where we are. So now we're right down to where we're accustomed to working. Up in the upper right-hand corner is this schematic window. And in the schematic window, there is a representation of the circuit as it sits right now. Any matching components that we add later will be added to the circuit. Just to look at what we have right now, on the right, we have the generator. That's the signal source, the radio, the transmitter, whatever your signal source happens to be. It could be a signal generator, it could be a radio transmitter, it could be an amplifier, but whatever your signal source happens to be, that's the generator. On the left is your ZL, or your load impedance, which would equate to, for example, the antenna. In the middle, you can see right here where it has Zin. Zin is right here and has an arrow pointing towards the load. Zin is the input impedance. What do you think our input impedance would be in this case if we're talking about a standard ham radio setup? Probably 50 ohms. The values shown right here, right now, are 33 minus J51 ohms, which is what we input into the system up here from the keyboard entry before. That's what it should be. That's what we input in, and that's what is represented, I should say, by this plotted point on the Smith chart. We determined earlier that the match that we were going to use with this was the match that used a shunt inductor and a series capacitor, and we say that the first thing that the load would see, looking into the coax, would be the shunt inductor. So that's going to be the first item that we put in. We'll come up here, and we'll get the shunt inductor. We'll click it, and then we'll come out to our point, and it has already prescribed an arc. We'll just follow that arc up till we hit the unity resistance circle, and we'll click right there at that junction where it hits the circle. You can see the arc that was drawn in there. We have a new temporary point here at TP2. The temporary point now shows a resistance of 49.6. I'm sorry, it's showing 48.538 plus J 45.451 ohms. So it's a plus J now because we're above the horizon. It's now an inductive load. Got a question for you. If we were to drop straight down from this point to the real axis, would that represent the resistance that we're seeing at that point? And the answer is no. The resistance that we're seeing at that point is represented by this unity resistance arc. That's the constant resistance circle, I should say, not arc. It's actually a circle. But any point on that circle has the same resistance. Any point on the red circle has the same resistance, which is called the unity resistance circle. This blue circle is the unity conductance circle. Any point along that circle will have the same conductance. And conductance, of course, as we saw earlier, is the opposite of resistance. The second component that we added earlier was a series capacitor. A series capacitor will rotate us counterclockwise on this constant resistance circle, or on this unity resistance circle, right back down to the prime center. So let's get a series capacitance, and let's do that. Let's take it down. Now, as you can see, I'm not at the prime center. I'm actually past it. And the reason for that is I clicked too far up. I didn't click on the circle here. That's why my reading is higher than I expected. I expected 46 ohms from my practice, and I got 48 ohms. So let's back these out. Let's back these out and redo the shunt and get it on the circle. All right, now we're at 50.122. That's about where I want it to be as far as the resistance is concerned. Now let's put in the series capacitor, and it takes us right down to the prime center. We end up with 50.122 plus a J 0.000. In other words, almost a perfect match. 50.122 ohms. That's negligible. And then no reactance whatsoever. So you can see that L match that we have depicted in this schematic up here perfectly matched this load, this antenna. Absolutely perfect. We did that with an L match that has a shunt inductance followed by a series capacitance. Funny thing here, as I recall, when we were working earlier, arithmetically we came up with, I believe, around 207 picofarads for our capacitance, and somewhere in the 500s on our inductance, 500 nanohenries. We're seeing just under 500 nanohenries here, but we actually came up with 207 picofarads. Those values are pretty close to what we calculated doing it on paper, doing it the old-fashioned way without using the software. It's kind of funny how close we can actually come. Suppose we want to do this a little bit differently. Suppose instead of going all the way up to the top part of this constant resistance or unity resistance circle, suppose I want to stop down here at the first place that I hit the circle. Could I do that? Could we still make it up to the prime center or home from there? We could. Well, let's try something different first. We'll come back to that. Let's take out these 2 points that we just put in, zoom out just a little bit, and we're going to try something different. We used a shunt inductor as the first component. Let's use those same 2 components, series capacitor and shunt inductor, but let's put them in the opposite sequence. Let's start with the series capacitor. Where does that take us? That will take us up here to the infinity point on the real axis. Interesting. So we are at 33 minus J 20450.043. In other words, over 20,000 ohms of resistance. Over 20,000 ohms of resistance is what we have here. So we need to get rid of that resistance. What would we do to get rid of that resistance? The answer is going to be that we have to use a resistance to do it. To get rid of that, to get rid of this extra resistance and get back to the prime center, we're going to need to add a resistance to this circuit. Now, that sounds funny. We're going to add resistance to get rid of resistance. But if you think about the theory of resistors in series and parallel, it makes perfect sense. We know from our studies that adding a resistor in parallel reduces the overall resistance. Let's see how much resistance we would need to add to bring that down to 50 ohms. So we're going to get a series now. No, we're not. Do we want a series or do we want a parallel resistance? I should have asked that first. Which do we want, series or parallel? We just said that using a parallel resistance reduces it. So we're going to use a parallel resistance here. Let's see how far we have to go. We have to go to a value of 50 ohms to get to the middle there. And we end up at 50 minus J 0.122. Very, very slightly capacitive. But we are at the prime center. Now that was an RC or a CR, capacitive resistive match. Capacitive and resistive match. Okay, let's go back to what we had said earlier. Let's take the two of them out. Let's go back to our shunt inductor that we used earlier, only this time, let's stop at that first crossing of the unity resistance circle. What do we need now to get us up to the prime center? What we need to do now is we need to add something that's going to rotate us counterclockwise on this circle, or clockwise rather, on this circle. Clockwise, we have to go clockwise on this circle to get up here. What might that be? Let's take a series inductor, and boom, there we are. So now we had a shunt inductor and a series inductor. This was one of those LL matches. 2.9 microhenries in shunt and 620.2 nanohenries in series, and we end up at 49.868 minus J 0.247, close as you want to get. So there's some different matches we've seen already. So now we've looked at a shunt inductor, a series resistor, a shunt inductor stopping short. Let's see what else we can do. Let's take the two of them out again. This time let's put in a series inductance. Where does that take us? Well, that can take us right to here, right to the real axis. Now what do we need to get to the prime center? Now we need to add a series resistance. We need to increase the resistance because we're below 50. So we need to increase the resistance. We're going to use a series resistance, and it's going to be 17 ohms that we need to get there. 17 ohms is what it took. So we had a series inductor and a series resistor. There's an LR match. Let's take that out. Let's try one more. Let's try the shunt capacitor as the first step. Where does that take us? That takes us all the way out here to the 0 point on the real axis. Now what do we need to add? Again, a series resistance. So let's get it. And how much do you think we're going to need? I'm betting on 50 ohms because we're going from the 0 right up to the middle. And here we go, 50 ohms. But we've seen several solutions that got us back to this point. Several solutions that got us back to that point. Suppose the first thing we were to put was a resistor. Shunt resistance takes us to the 0 end. Now we need to put a serial resistor to get back to the center. So we could have done this just with two resistors. That's a rather unorthodox method. Can we do it the other way as well? Of course we can. Let's go with the shunt resistor, or the series resistor first. Series resistor first takes us up to here, and now we need a shunt resistor to take us back to the center. So we've seen LC, RC, and RR matches, and we saw an LL match. The point of the matter is that you can do almost anything using the components on hand, using those three components. Here's the one thing that you have to remember. Although we brought our resistance, our impedance back to the prime center, have we really canceled out the reactance? Let's look at our result right now. Our result says 50 minus J 0.00000 with a Q of 0.000. Absolutely perfect, right dead on the money. So yes, we did cancel out the reactance. And we did that just using resistors. That is very, very unorthodox. It's very seldom done. But it can be done. All right. Let's move on a little bit. We said earlier that there were also CC matches. Would a CC match work here? Well, we already saw that both ways I tried to put a capacitor as the first component. It only took us to the real axis. It didn't let us get to where we could use a second capacitor. So no, a CC match would not work here. But if you think about where our point is plotted, if you remember earlier, we saw the diagram that had the top half, these two circles and this top side all in green and this little bit in yellow, and we said that was the LL match territory. And when these two circles were in green and this side was in green and this was in yellow up top, then we said that was the capacitive correction area. Why? Because any point up in that area up here is an inductive point and therefore needs capacitance to correct it. And any point down in this portion is going to be capacitive and therefore needs inductance, to correct it. So a CC match would not work down here. A CL, a CR, they do match, but CC would not work. The only place a CC match would work is if you were in this area bounded by that arc, and this arc. This top area here is the only place that a CC match would work. We've seen several different approaches, and we've been working with the same point that we have been plotting all along. Let's make some differences. Let's change some things around. Let's give us a different value to start with. Let's get rid of this point and put in a new point, and let's make it 158 ohms with a J of 97. Let's see where that gets us. Wow. All right. 158 ohms and a J of 97. Clearly it's inductive. Will a CC match work on that? It is inductive. Will a CC match work? No, because it's outside of this top side shaped area. It's into what would have been a green area on that CC chart. So a CC match will not work. So where do we want to start? Well, let's start out with Old Faithful. Let's start out with a series inductance and see where that takes us. A series inductance takes us over to to infinity on the real axis. From which point, what do we need? We know that we need a parallel resistance to get back. And there we go. Suppose we start with a shunt inductance. Yes, the shunt inductance takes us along this arc over to the 0 point. Now what do we need? Now we need a series resistance. And a series resistance takes us to the prime center. So far, it seems to be pretty much the same type of a setup, doesn't it? Suppose we tried to start out with a series capacitor. A series capacitor, where would that take us? Why, that would take us around to the real axis, but not as far around. Now we would need again a shunt inductor, or shunt resistor rather. And now instead of 50 ohms, now we need more. Now we need 73 ohms, almost 74 ohms to get there. If you notice from this end, we needed 50 to get there. Now here in the middle, we need 74. We need more because we're not at the end. Doesn't make common sense, does it? But that's the way it works. All right, let's go with the shunt capacitor as our first device. It takes us down here to the constant resistance circle or the unity resistance circle, at which point we can now use a series inductor to bring us right up to the prime center again. Every one of these are easily done this way. Let me ask you a silly question. Suppose I were to have put my shunt capacitance, just as I did here, and then to that, I added a shunt inductor. Where would that take us? That would take us all the way around to here. Now what do I need? The shunt inductor basically just reversed what the capacitor had done because it took us right back to our original point. Now we need a resistance again. So that capacitor is just along for the ride and is not really doing anything. When we took that point all the way down to here with the capacitance, and then we added the shunt inductor, it canceled out that much of the capacitance and then continued on around to this point, where again we need a series resistance now to bring us back to prime center. This tool is handy because it lets you see all the different ways that you can build matching networks for almost any situation you can get into. We'll talk more about the software in a little bit. I want you to see it. I want you to see it in use. I like this software. It's a nice platform. It's not the only one available, but this is one that I like and the one that I have to use because of the type of computer I have. We'll talk more about that later as well. That's it for this little video. I didn't want to make it too long, but that'll do us. So let's close out the application, and we're done. Thank you very much.